have Kaavya Sahay. She is from Yale, working in the Prairie Group. She's a senior graduate student, and she's gonna show us her work on quantum error correction. So please welcome Kaavya.
Thank you very much for the invitation. As Alex introduced, my name is Kaavya Sahay, and I am a graduate student working with Shruti Puri at the Yale Quantum Institute in quantum error correction. Today, I'll be talking about two projects that I've been a part of that are in the general area of designing QEC protocols to tailor them to hardware and improve performance. At any time during this talk, if you have a question, please feel free to interrupt me and ask. So I'm just going to flash this statement on the screen, and we're not going to go too much into detail as to why this is true during this talk, but let's take it as a given that if you have a large-scale quantum computer with enough qubits and the ability to do enough operations, it will be able to solve a problem that is intractable to today's classical computers. What is a small part of this computer going to look like? It's going to consist of a quantum circuit, such as the one shown. You have qubits going through different kinds of operations. And when you scale this up, you're going to increase the number of qubits, and you're also going to increase the number of operations that your qubits are undergoing. Now, when you reach a quantum computer of a large enough scale, the error rates required from every component of the circuit are approximately of the order of 1 in a trillion. And this is so low because you want your large quantum computer to successfully give you the meaningful result at the end of this large computation. Unfortunately, the components that we have in today's hardware, they have failure rates of the order of 0.1%, 1%, or even higher, as people who are close to the experiment will very well know. Another challenge that quantum computers face is that it's fairly easy for me to draw a multi-qubit gate, such as the one I've drawn here, which goes across several qubits. But in actuality, our hardware often has restricted connectivity, and doing these long-range interactions may not be as easy as drawing them on a piece of paper. And so these are the two central challenges that I'm going to be talking about in some detail today. In terms of the first challenge, we have the fact that physical qubits experience noise, that is, they decohere. For example, you have our qubit subspace. We see that there are several different types of decoherence. You have errors which move you around inside the qubit subspace, and you also have errors that take you outside the qubit subspace into an entirely different part of the physical Hilbert space. And the central idea that we're going to use to address this challenge is that some forms of noise are easier to correct than others. And so it is advantageous to you if you're able to engineer your qubits or choose qubits that have tailored noise channels such that they experience the forms of noise that are easier to correct. The second challenge that quantum computing experiences is that hardware has restricted connectivity, and you can only have a very, very limited set of kind of connections that you have between qubits. For example, in some non-local architectures, you have two arrays of qubits. One is the grid-like array and one is the green array. And you may have some ability to move one array past another or do some restricted set of long-range connections. And we're going to explore briefly how we can exploit certain realistic interactions that hardware can realize in order to improve QEC performance. I won't be addressing these two challenges in a very broad scale. I'll be addressing them in the specific context of the quantum error correcting code, the surface code, which is a very popular choice in today's NISQ era. So here I have shown you an example of a distance 5 surface code. Why is it a distance 5 surface code? Because it is a grid of 5 by 5 qubits. So you have 25 physical qubits. The 25 physical qubits here are used to protect 1 degree of logical information, which is called your logical qubit. And this protection is such that in order to corrupt or flip your logical information, you need Z errors to span horizontally across the lattice, or you need X errors to span vertically across the lattice. These are the only options that will cause your logical information to be corrupted. Your underlying physical qubits can experience errors, and we use what we call stabilizers to detect these errors. So every loose square on the surface code is a Z stabilizer, which is the product of 4 Z operators on the surrounding corners of that square. And every red square is an X stabilizer, which is the product of 4 X operators on its corners. For example, let's say that an X error on the surface code happened on that physical qubit in the bulk. When we measure the stabilizers surrounding it, we see that the X error anti-commutes with the Z stabilizers immediately adjacent to it. So X and Z anti-commute. And when you measure that Z stabilizer, you get a -1 outcome. These -1 outcomes are commonly known in the quantum error correction field as syndromes or defects. So here you have 2 defects arising from the adjacent anti-commuting stabilizers. When you measure the X stabilizers next to that X error, X and X commute, so you don't see any defects on those stabilizers. Similarly, if you had a Z error somewhere on your surface code, then you would see a defect on the adjacent X stabilizer. So your physical qubits continue to experience errors. You measure these stabilizers and collect defect information. And then what you can do with your surface code is that you can use this defect information in order to apply corrections. The idea being that after applying these corrections, you only fail if your physical errors are on the order of the size of half the distance of your code. So for your distance 5 code, what this means that any combination of 1 error or 2 errors you can correct. But once you start seeing 3, 4, or 5 errors on this surface code, you start being unable to correct your logical qubit state. And therefore, this gives us the intuition that if you have a low enough physical error rate, then with a large enough logical qubit or surface code, you can create a logical qubit that is protected up to an arbitrary degree. Hopefully this is clear. And what we're going to do, or what the idea of quantum error corrected computation is that we take our quantum circuit and every qubit, which was before perhaps we imagined it as a physical qubit, it is instead going to be a logical qubit that we feed into our quantum circuit. So now that we have a primer on the kind of computation we're doing quantum computation with error correction codes, let's go back to our central challenges and talk about how we're going to address them specifically. In terms of tailoring noise channels, I will specifically talk about the example of biased erasure noise, which is a natural noise channel for neutral atom qubits. And then in terms of exploring realistic non-local interactions, I will talk about a specific protocol that is called magic state cultivation. Before I move on, are there any questions about the surface code? All right, great. So starting off with biased erasures. So the examples I gave you before with the surface code, you saw that when we looked at these particular errors, the X error gave you defect information, but there was otherwise no information given to you by that physical qubit itself that it experienced an error. You had to measure the stabilizers, and then you knew that an error had happened. In contrast, let us imagine we have an erasure error. What is an erasure error? It is a detectable error at a known location. So again, you have your qubit subspace, and this qubit subspace has a dominant error channel where it decays to an external state. Importantly, this external state is detectable, i.e. you can image it without disturbing the qubit subspace. And if you image it and you see population in this leakage space, then you know that your qubit has experienced an error. And so you can flag it as being untrustworthy. There's been a lot of work on erasure qubits that has been done in the superconducting community at Yale and at, for example, Amazon. But erasure qubits, and specifically the dual real form of erasure qubits, date back much further into optics, where you have linear dual real qubits. Now that we kind of have a basis to understand erasure qubits. Now let's move forward into biased erasure qubits. A biased erasure qubit is one that experiences an erasure only from a known state. For example, again, we have our qubit subspace and our leakage subspace. But now the coupling of this qubit to the leakage subspace is only from one state. The 0 state cannot leak, but the 1 state can still leak. And this is what denotes our biased erasure noise. This is a nice theoretical picture to have, but let's see how it actually arises in specific platforms, such as neutral atoms, specifically the metastable ytterbium atom. So here we have, again, our qubit subspace with the 0 and 1 states. And in this metastable atom, the qubit subspace is fairly stable, so it can stay coherent for quite a long time. The dominant errors actually happen when we perform gates. And we perform gates by exciting the 1 state to a higher atomic level, called the Rydberg level, and then having this atom interact with a similarly excited atom in the Rydberg level, and therefore acquiring a phase. Once this atom is in the Rydberg level, the dominant error mechanism is decay from the Rydberg level to other states, which can be imaged. And once you image these states, you know that this qubit has experienced an error. Importantly, because only the 1 state is coupled to the Rydberg level, and only the Rydberg level decays to external levels, as soon as you image these external levels, it is like you have measured your qubit in the Z basis, identifying that it was in the 1 state. As a result, you can perform the reset operation, where you put your qubit back in the 1 state. This is the basic channel of a reset into 1. I minus Z is the 1 state. When we Pauli tool this, we can get the following channel. A Pauli tool is when you simply remove the off-diagonal terms and leave the on-diagonal terms. So we get the blue equation from the equation above it. And you can see that the blue equation is simply a heralded identity or Z error. As a result, whenever you see population in this external state and you reset, you know that you have either restored your qubit state or you have done a Z error. One of the two options with 50% probability to your qubit. Similarly, for unbiased erasures, we can go through a similar proof to understand that when you have an unbiased erasure, you cause I, X, Y, or Z with equal probabilities. So now that we understand what a biased erasure is and how it is physically realized in certain systems, let's think about why it offers us an advantage in terms of error correction. So I'm going to go through several different forms of noise in this simple error correcting code, the repetition code. Here we have 3 physical qubits, which are the white circles, and 2 stabilizers, the XX stabilizers. Here, the logical qubit has a single qubit logical X operator. So if we have an X anywhere in our code, that will flip the logical degree of freedom that we were trying to protect. But we need 3 Z's to flip the logical degree of freedom that we were trying to protect. So first, let's imagine that we just had this X operator that I talked about. This will indeed corrupt your logical information. And additionally, it gives us no stabilizer information because our X stabilizers commute with this X errors. So if we have dominant X noise or bit flip noise, then our probability of a logical error scales with the physical error rate P. Let's move on to another form of error, which is Z noise. Let's say that we had this Z error and we measure our stabilizers. A stabilizer that is adjacent to this Z error will give us a -1 outcome. The other one will give us a +1 outcome. And so using this defect information, we can probably identify that the error that happened was indeed this error on the left. The case where we guess wrong is where if we had instead 2 Z errors on the right qubits, which would give the same defect information because the 2 Z errors surrounding the right stabilizer both collectively commute with the right-hand side stabilizer. And only the left-hand side stabilizer has an odd support of Z errors. As a result, we need 2 Z errors in order to apply the wrong correction because we guessed wrongly about the error that was happening. And so our protection to phase flip or Z errors scales as P squared with the physical error rate. Let's reset again. And imagine now we had an erasure, or specifically a biased erasure. Our leftmost qubit has now leaked to an external state, and we have imaged and replaced it. And we know that our biased erasure causes identity or Z with 50% probability. What we can now do is that we can measure the stabilizers. If the stabilizers give us all +1 outcomes or no defects, we know that we have correctly restored the logical state. If our stabilizer outcome gives us a -1 on this particular stabilizer, we know that this biased erasure led to the introduction of a Z error. The only case where all of our qubits could suffer biased erasures and we actually guess wrongly about the state that we had to restore is if all 3 of our qubits suffered this form of error. And so our protection to logical errors scales as P cubed and is suppressed compared to the previous error modes. Let us reset again and imagine that we had, again, an erasure on our leftmost qubit, but this time it's not a biased erasure, it's a conventional unbiased erasure, which could have given rise to I, X, Y, or Z. What could have happened in this case is that we could have had, out of these 4 options, the X error happen. And if the X error did happen, then we have no stabilizer information to guess about the error, and we will potentially suffer a logical error because of this uncertainty. The only difference between case 4, which is conventional erasure, and case 1 is that in case 4, we have some information about something having gone wrong because we have detected this leakage outside the computational subspace. So hopefully this is a good primer as to why biased erasures might be good for us. Biased erasures give you knowledge about the error location, which we don't know for polynoise. We have to guess about the error location from polynoise based on the stabilizer information and the defects. And biased erasures also give you information about the error type, which is identity or Z, versus unbiased erasures, which could give you all 4 kinds of poly errors. So now let's move on to biased erasures in the surface code. And before doing that, I'll draw your attention to the form of what we call logical operators in the surface code. In order to corrupt this logical degree of freedom that we are trying to protect, we have 5 Z's needed and 5 X's needed. Let's suppose our hardware was our model where we experienced more Z's than X's. One could imagine, in this case, we don't need that much protection to X errors because X errors happen less often. And so we could use a thinner surface code, which has less vertical depth, in order to protect our logical information, to prioritize protection against Z errors compared to protection against X errors. And it looks like, almost based on our previous discussion, that biased erasures might be a good setting for this because it seems like biased erasures only introduce Z errors. But let's go closer and see what's actually happening with the surface code. So in order to measure these stabilizers, the 4-body operators that I was talking about earlier, we actually have to use a series of 2-qubit gates. So we initialize an ancilla qubit in the plus state and perform a series of 4 CZ gates with the 4 qubits in the corners before measuring out the ancilla qubit. And that gives you this 4-body ZZ information. Let's say that these biased erasures could happen at any point after these 2-qubit gates. So you image your qubits after every 2-qubit gate. And at some point you detected an error, you reset the atom in the 1 state, and then you will see that you have introduced an identity or a Z with 50% probability. So far, so good. We wanted only Z errors, and we have introduced only Z errors. But now let's go into the measurement of X stabilizers. This one was the measurement of a Z stabilizer. When we're trying to measure X stabilizers, we have to use a series of control NOT gates to measure the 4-body X stabilizer. In certain hardwares, actually in many hardwares, you do not have native CZ gates. C0 gates. You have native CZ gates, which you have to conjugate with single qubit Clifford gates, the higher mod. So what happens here? Again, you can image your qubits after your gates to identify whether biased erasures have happened. If an erasure has happened, you reset it. And before this Hadamard, you had possibly introduced a Z error. But what does this Hadamard do? The Hadamard converts the Z error into an X error. And so now you have both Z errors and X errors in your surface code as a result of this biased erasure channel. And so this ideal property that we wanted in terms of only having Z noise and being able to use a thinner code with fewer physical qubits may not be achievable with this kind of error model. Nevertheless, let's try and study the surface code numerically under structured noise models and see if there's still an advantage to biased erasures. So we take a certain error model where gates can experience errors at the rate T, and a fraction of them could be erasures, and the remainder are depolarizing polynoise, which do not give you these flags about their occurrence on that particular qubit. And we use a particular correction algorithm using a minimum weight perfect matching. The results we get are as followed. On the y-axis, you have the threshold error rate, which gives you an idea of how many errors this code can correct. And on the x-axis is the erasure fraction, going from 0 on the left, which is all polynoise, to 1 on the right, which is all erasures. And we see, surprisingly, that there is a difference between biased erasures and unbiased erasures. So on the left, where we have all polynoise, our threshold is 1%, which means that we need all of our components to fail at a rate of less than 1% in order to succeed in our logical computation. On the right, where we have all erasures, our threshold for unbiased erasures is 5%, but our threshold for biased erasures is about 10%. What does this mean? This means that if we had a surface code and our components failed at a rate of 7%, we would have no hope of succeeding if these error mechanisms were unbiased erasures, but it is possible for us to successfully, potentially, conduct a logical operation if our errors were biased erasures with a 7% failure probability. Why is this true? This is true because of a reduced noise entropy. What does that mean? It means that when biased erasures occur, if they occur during a Z stabilizer measurement, we know that they have introduced Z errors, versus if they have happened during an X stabilizer measurement, we know that they have introduced X errors. And so we can tailor our correction algorithm to use that information during correction of these biased erasures. However, for unbiased erasures, we have no information about the error type that is happening, and so we are unable to make that kind of tailored correction algorithm in this case. And that is why we see these different thresholds. Another subtle thing that I'll point out is that for polynoise, your logical error rate generally scales as half the distance of the code, but when you have biased or unbiased erasures, your logical error rate can scale up to the full distance of the code, which gives you an additional advantage in terms of error suppression that you see with these surface codes. Now going slightly back to our physical system, in the ytterbium atom that I mentioned earlier, your erasure fraction is not generally all the way at 1. There are some residual poly errors, and your erasure fraction, i.e. the percentage of erasures that you see, is 98%. At 98% erasures, your threshold to biased erasures is 8%, and your threshold to unbiased erasures is 4%, which is still, as you can see, a huge improvement over the case where your qubits experienced only polynoise. This is good, but if you recall, our goal was originally to use a thin code so that we didn't have to use so many qubits to protect one logical degree of freedom. And we did find a way to solve that. We called it the hybrid fusion construction. And when we use the hybrid fusion construction, our threshold error rate goes up to almost 18%. I won't go into too much further detail about this today, but if you're interested, please feel free to chat with me afterwards. So this, in fact, brings me to the end of the first part of my talk, where I talk about structured noise channels. And I will pause for a second here if anyone has questions. Sure.
When you do imaging to see whether an erasure has occurred, does that affect the computation at all?
Great question. Yes, it can. And so a big part of engineering these erasure qubits is to make sure that you also have the ability to do fast and non-destructive erasure checks. Because if your erasure check takes too long, then your qubit can decohere while this is happening. And if your erasure check disturbs the qubit subspace, then you might be introducing more noise than you're taking away. Cool. Moving on. So we discussed fast erasures, and now I will move on to magic state cultivation. Before doing that, I'm going to do a brief return to this circuit that I showed you earlier, where we have our logical quantum circuit, where we have input instead of bare physical qubits, different surface codes. There is a select number or kind of gates that I've shown here on this quantum circuit, and they are the Clifford gates, which include CNOT, Hadamard, and Pauli's. It turns out that if you have a quantum circuit with only Clifford gates, then any such quantum circuit is easily classically simulatable. So you cannot get quantum advantage from this kind of circuit. When can you get quantum advantage from a circuit? When you include non-Clifford gates, such as the T gate or CCZ gate. So let's put them back into our logical quantum circuit. The problem now is that these particular kinds of gates are quite difficult to perform fault tolerantly on the surface code. And what do I mean by that? Your surface code is designed to protect you against a certain number of errors. But trying to perform these gates on the surface code destroys that error protection. And oftentimes, if you try to perform these gates, one or order one errors can corrupt your logical state. This is obviously undesirable for fault-tolerant quantum computation. There have been some efforts to address this and create fault-tolerant non-Clifford gates, such as the T gate. And there's been some recent work on this, but this is still in the very theoretical proposal stage, and practical numerical studies of these proposals has yet to be performed. Instead, what the community has resorted to is the following. You prepare a surface code that is already in the state that it would have been if a T gate had already acted on it. And then you entangle that with the surface code already in your logical quantum algorithm, represented by the top surface code, using a Clifford gate. And then you measure out the first surface code. So what we have done here, we have pushed the problem of performing a fault-tolerant T gate onto a surface code into the problem of creating a high-fidelity surface code state that acts like the T gate has already been performed on it. So these states are called magic states. And what is, again, the problem with this, or the central difficulty with generating these magic states? That is, your physical error rates are pretty high, of the order of 1%, but the magic states fidelity that you want is on the order of 1 in a trillion for certain kinds of states, which translates to about 10 to the minus 7 for these T states in particular that we're interested in. So on this topic, there has been a recent proposal called magic state cultivation by Gidney and co-authors that is, in summary, a low overhead way of preparing high fidelity magic states. And what is the overview of how cultivation works? It's as follows. So first you inject your T state into a small code to prepare a logical T state in this surface code. This is a different surface code variant, which I will be briefly addressing later. But the idea here is that this injection operation can be noisy. Your logical state may be corrupted linearly with the physical error rate, but you have prepared some kind of logical state. Next, you cultivate, i.e. the key step of cultivation, your logical state. What does it mean to cultivate a logical state? You perform a series of stabilizer measurements and logical checks of the state encoded in the surface code to ascertain whether or not you have indeed prepared the state that you wanted to. With the idea being that if you have any checks that fail or any stabilizer measurements that return you -1 outcomes or defects instead of +1 outcomes, you choose to discard that state and restart the protocol to try and get a pure state instead. Once you have done enough of these stabilizer measurements and logical checks, the idea is that you have now produced a magic state whose logical failure rate scales with the distance of the code as p to the d1. However, if you can recall, a code of size d1 can only correct up to about d1 by 2 errors. And so if you stay in the small code size, it is possible that you can accumulate additional errors and destroy the scaling. So this scaling is in fact fragile. And so the next step of cultivation is called escape, where we quickly grow into a larger code size of size d2, such that our magic state is now sufficiently protected by the larger distance code from subsequent errors. I'm going to pause here for a second. We'll be going over this again in a different form, but the summary is that magic state cultivation has 3 main stages: injection, cultivation, and escape. What we can further do on this after this escape stage is we can perform error correction algorithms on our larger code and discard this larger state using output that our correction algorithm gives us. Great. So in terms of this general overview, what does magic state cultivation performance look like? It's as follows. So on the y-axis, you have the logical error rate, going from about 10 to the -3 all the way down to 10 to the -10 for certain cultivation protocols. And the x-axis is the number of expected attempts. What does that mean? Is that whenever you're cultivating, some shots you'll have to throw away because they have returned you -1 stabilizer outcomes or your logical checks have failed due to errors. And therefore, in order to produce a state with sufficiently high fidelity, you might have to try a certain number of times before you succeed. The curves also span a range in the space because there's a corresponding varying amount of post-selection that you'll have to do in order to achieve a state of a sufficiently high logical fidelity. And there are 2 broad groupings of curves that you can observe. One is producing magic states that scale cubically in the physical error rate, and one is producing magic states that scale to the 5th power in the physical error rate. The curves I've shown you here are from 2 prior proposals. The blue one is from Gidney and co-authors, which uses purely local interactions between qubits. And the subsequent one is from Chen and co-authors that is able to achieve lower overhead because they use lower number of expected attempts in order to achieve a state of a given fidelity. However, they use non-local interactions that may not be physical for several kinds of qubit architectures. In our work, we achieved the following performance. So for our cubically scaling logical error rates, you can see that our curves are slightly to the left of previous proposals, therefore reducing space-time overhead correspondingly. And for our logical error rate scaling to the 5th power proposal, you see that we're significantly to the left of prior proposals, also improving on the expected attempts and the space-time overhead. So this is how our protocol does. How does it exactly work and why does it perform better? Let's go through that next. I'll also draw to your attention 2 parallel proposals from Vaknin and co-authors and Jehan Theis, who also propose certain magic state cultivation variants. All right, so the high-level summary of our protocol. We inject our magic state into the rotated surface code of distance 3. This is a picture of the rotated surface code that I've shown you several times before, except it's now a smaller one. It's a lattice size 3 by 3 instead of 5 by 5. Then we measure the stabilizers. If any stabilizer measurements return a -1 outcome due to errors that have happened during this process, we choose to discard the state and try again. Now is a non-trivial step where we grow from this rotated surface code into a regular surface. So the 45-degree rotated version of the lattice you see on the left, which has now appeared, is called the regular surface code. It also has the ability to protect you up to 3 errors. Once we're at the regular 3 surface code, we perform logical checks, i.e., we try to ascertain whether we've actually prepared the T state or we prepared something else entirely. If any of our logical states fail, then we discard the state and we try from the beginning once again. After the logical checks, we do more stabilizer measurements, trying to see if our logical checks have now introduced errors. If the stabilizer measurements fail, again, discard the state. Now we are in the regular surface code, but we actually wanted to be or doing our computation using the rotated surface code. And so we perform a short step unitary circuit to go back to the rotated surface code, but now with a distance 5 instead of 3. After we're at this distance 5 surface code, we do more stabilizer measurements and slowly grow our code before using unitary growth to escape to this code size that we actually want for our logical quantum computation. So this is a lot of steps, and I'm going to go through the key parts of our protocol that actually help us do this efficiently one by one. The first key is efficient code conversion. So as you saw, we were moving between the rotated surface code and the regular surface code. Why do we do this? Because we want to perform logical checks, and the ability to do these logical checks efficiently is not present in the rotated surface code, but it is present in the regular surface code, which is why we have to move between one and the other as part of our protocol. And how do we do this? We start off with our rotated surface code, and there exists a depth 2 circuit, so just 2 layer of gates, that can take us from a regular surface code to from a rotated surface code to its corresponding regular surface code. So we introduce more qubits at the centers of the stabilizers and perform 2 layers of entangling gates. And after these 2 layers of entangling gates, your total system is in the state of this regular surface code. Before I describe the logical checks, let me also make the point that now that we've entered this regular surface code, we wanted to go back to the rotated surface code of a slightly higher size. And indeed, there is a short depth unitary circuit that looks pretty similar that takes you from the regular surface code to a slightly bigger rotated surface code. The idea being that because we have these short depth circuits, it's fairly easy to move between these different codes. The second key part of our protocol was the logical checks. And let me take a step back and look at the circuit that is shown at the top of this slide. Let us say you have the eigenstate of an operator O, and you want to ascertain whether you actually have prepared that eigenstate or you prepared something else. You can do this by using a form of the Hadamard test, where you take an ancilla and perform a controlled unitary operation O on your state using the ancilla before measuring out your ancilla. If your ancilla measurement gives you a +1 outcome, then you know that you have actually prepared the state that you wanted to. Or possibly, there was also an error, along with being an error in your state, there was also an error in your ancilla that made you believe you had prepared the correct state, but you have not. Alternatively, if you see a -1 outcome, you know that you prepared the incorrect state and you can discard it and try again. So for us, we have prepared this regular surface code in this T state. So we want to perform the unitary T on this regular surface code. What does the unitary T look like on this surface code? It's not as simple as doing T gates on all the qubits. It is in fact this series of gates where you do these Clifford gates on the diagonal qubits, and you do control Z gates on the off diagonal qubits across the diagonal. So that is the equivalent of that box O that we have on the circuit on the left. And then we want to control this using an ancilla. So we introduce a GHZ state and we do controlled operations. Notice that because we have CZ gates as part of the unitary, we're going to have to do a control Z gate on our surface code, which is a non-Clifford gate needed for our protocol. So these are the two almost key parts. And now let's go back to our protocol. You can see there's several points at which we use these unitary code conversion circuits that I just showed you, where we move between rotated and regular, and then regular and rotated surface codes. And because they can be done in short depth, we're improving the overhead of our protocol. And further, we have these logical checks, which require non-local interactions, but only across a distance 3 or possibly a distance 5 surface code, and are therefore also relatively easy to achieve in non-local architectures. And apart from these 2 steps, or these 4 steps that I've highlighted, basically every other part of our protocol is stabilizer measurements, which are known to be of depth 4 for the surface code. Recall I showed you earlier a sequence of 4 gates that gave us a stabilizer measurement for a surface code. So you can see that all of our protocol is highly optimized and tailored to the surface code without incurring the overhead of a large number of gates or any other kind of code conversion that you might need to do in order to prepare a high fidelity magic state. And so this is in fact what allows us to get the improved performance that we saw in comparison to previous works. And just to give you an idea of why we see the performance that we do for previous works, Gidney et al. Focused on using local interactions on a purely 2D planar architecture. And as a result, they choose to inject into a different kind of code called the steam code instead of the surface code. And because they inject into the steam code, they have to do quite a bit of code selection and error correction tricks in order to grow to a larger size surface code. In Chen et al.'s work, they do use local interactions, but once again, they do not try and inject into a surface code or do these logical checks in the surface code. They do it on a different code family that they refer to as the RP2 code family. And again, there's some parallel works that you can explore if you have an interest in them, and they achieve work performance that is similar to Chen and Gidney on this performance landscape. So with that, I have come to the end of my talk. We have presented an optimal structured noise tunnel, which is biased erasure errors. And using biased erasure errors, we have shown that you can improve quantum error correction thresholds because you're getting more information about the errors that are happening. And secondly, we have exploited these kind of realistic non-local interactions that are present in certain architectures in order to prepare a high fidelity magic state that takes very low space-time overhead in comparison to previous works. And these high fidelity magic states can be used as input for logical quantum algorithms in order to conduct large-scale quantum computation. There's a few different ways that these specific directions of research can be extended. Firstly, I focused very heavily on surface code today, which is a popular near-term quantum error correction code. But there are also a larger family of codes known as low density parity check codes, which achieve a higher encoding rate, i.e. they use less physical qubits per logical qubit than the surface code. And extending these methods and tailoring them to LDPC codes is an active and quite interesting direction of research that can be taken. Secondly, we have focused very much on these kind of nice error models of poly errors or erasures. Whereas in hardware, what often happens is that your errors may not be so friendly to your correction of them. So you may experience a form of physical noise known as leakage, where your qubit escapes the computational subspace, but you actually have no way of telling that this has happened. And this often tends to be the most damaging kind of error for quantum error correction. So investigating the impact of this physical noise channel on these protocols may also be a very relevant direction of research for quantum error correction. With the ultimate aim being, of course, that we would like to achieve logical qubits that achieve high fidelity with the lowest space-time overhead possible in order to conduct a logical quantum computation. With that, I thank you all for your attention and for many questions.
So this may be a naive question, but in terms of translating this onto physical hardware, you mentioned like these unitary growth stages until you get to the size of logical qubit that you want. And so seeing that is some conglomerate of physical qubits, what is do you foresee some sort of limitations in just the interactions between multiple qubits kind of scaling up as you make these larger logical qubits in physical systems?
That's a great question. So let me answer that in terms of a few different architectures. So for fixed qubit architectures, that is impossible, right? If you have a 2D planar chip in which you have qubits just on that chip, you cannot do that. So that's a hard limit that I think, for example, Gidney's protocol takes into account. Now let's talk about, let's say, neutral atoms and trapped ions. in these kind of architectures, you often have the atoms or ions held in place with magnetic fields or lasers, and they move around. But every movement comes with a chance of let's say, the atom being lost during the movement or the atom decohering during the movement. So there is a penalty to these movements. You would like to have these movements also be kept on the shorter range. And so that's the answer for these two architectures. Then there's a third architecture, which is photonic qubits. In photonic qubits, you have photons just traveling through their respective rails. And in photonic quantum computing, you expect the loss for distance travel to be quite small. So we don't anticipate this to be a limiting factor necessarily for photonic quantum computing.
Sure.
So perhaps the Chen et al. Proposal may be more suitable for that architecture, whereas our protocol is more suitable for maybe these other architectures I just mentioned.
Sure. Do you have some intuition for why you do this growing instead of just be another naive?
Great question. Why do we want to grow? Like, why do we want to go to that larger code size? Is that your question?
Or why? Yeah, what's the intuition behind the design, I guess?
I see. So ultimately, in a logical quantum algorithm, we want to use a larger distance service code. And we want to use a larger distance service code, but it protects us against the most errors. So the goal is always to reach the code on the right. Why do we do everything else at a smaller code size? Because we want to reduce the overhead. If something goes wrong at this code size, we can throw away this code, and we've only thrown away a small number of qubits. So we want to keep everything on the left as small as possible, but we want to keep everything on the right to be of sufficient size such that it can protect our logical qubit from errors during the quantum algorithm, which is why we go through this very careful growth, where we try to minimize the code size at every stage, but then maximize it right at the end.
And is like the 357, because D is arbitrary, right?
Yes, that's correct.
But the 357 is fixed.
That's a great question. So this specific summary that I've shown you on this slide prepares a magic state that will get you the best scaling of p to the q. And for that specific desired scaling, the 357 give you pretty good performance. You need the 3. You could do something with the 5 where you replace the 5 with 7 or 9. It has to be bigger than 3. And again, the 7 you could replace with bigger if you wanted to. But starting with 3 and moving on to bigger code sizes will always give you 3. You could replace some of the code size 3 used in these stages with a distance 5. And by replacing that with a distance 5 is how you get these curves on the right. Does that make sense? Great. If there's no further questions, I will move on to my acknowledgements. I'd just like to thank everyone in my advisor Shruti Puri's group. There were a bunch of collaborators on these projects. They're all listed on the left. And we also had external collaborators with Princeton, where we worked with Jungwon, and advisor there was Jeff. So thank you once again.
Well, thank Kaavya one more time.